Okay, so that was the idea about the behind the Prim's algorithm, and also intuitively why it is correct. Okay, so let's now look at the implementation of the Prim's algorithm, how we really converted this high-level pseudocode to a real algorithm. Okay, now if we look at this algorithm, okay, what do we need to do? So here I'm maintaining the outside nodes that I haven't reached yet. Okay, and what I need to do is that at any moment I need to, in each iteration of the while loop, so we're growing this tree. Okay, in any iteration we need to find the minimal weight crossing edge. Okay, so this is S. From S to U means it's a crossing edge. Okay, so naive implementation of this stage, we could simply, this step can be implemented simply by a linear scan of all edges. Right? I just scan all the edges, I check who are the crossing edges, and then among all the crossing edges, I maintain the smallest weight. It's just like a minimum operation. So it takes, this takes time, order of E for each scan, okay? And everything else is not a problem. We can then do that easily, okay? So this is a main step that we need a non-constant time, okay? So it takes time E. How many iterations can the while loop have? Well, you start with only the node V1. You pick one node, it's in your set S, and everything else you have not yet reached. And then you start to grow the tree. Every time you perform one iteration of the while loop, you reach one more node outside. Okay, so the number of nodes outside reduced by 1. So the number of iteration is exactly V minus 1. Okay, so the number of iteration of the while loop is V minus 1. Okay, so the total time complexity is as such V times E, if we use this very naive implementation. Okay, all right. So I can just, I don't need to do anything. It's very easy. I just every time scan all the edges and find the smallest crossing edge, weight crossing edge, and then I add it and then repeat. I repeat this order of V times. That's it. Okay. All right. But this is not very, this is what I'm putting here. This is not very efficient. Okay. So can we do better? Okay. Now, first, note that we're scanning all the crossing edges at each time, every time, okay? But actually, we didn't have to scan all the edges. What we could do is that, very similar to Dijkstra algorithm, we could actually store costs at nodes, okay? So in other words, at any moment, every nodes maintain a cost, which is, what is the cheapest way to reach me from nodes that's already visited in S? Okay, so so let's say that suppose you have already computed, this is just a random example, may not be correct, okay? So suppose you have already computed, visited all the nodes in S, and at any moment, each of the nodes remember that what is the cheapest way to reach me from nodes in S, okay? So for example, if all the red nodes are already in S, okay, then for V7, the cheapest way to reach V7 is basically, what are the crossing edges that reaches here? There are 2 crossing edges, 1 and 3. Then V7 says that, okay, the cheapest way to reach me is 1. That's the cheapest crossing edge that reaches me, okay? For V5, it would remember the cost. It said, okay, the cheapest way, there's only one choice, is 5. In this case, V3, remember 7. And at this point, V9, I cannot yet reach V9 using any crossing edge. So right at this point, would have infinity. Okay, same for V8, would also have infinity. Okay, so what we're going to do is that every node remember what is the cheapest way to reach me. Okay, now this is very similar to Dijkstra, where every node remember what is the shortest path so far, and the shortest of any path that we found so far to reach this reach me. Okay, there we maintain this estimate distance. Here we maintain the estimate costs. Okay, all right. Okay, and now here is the modified high-level outline. Again, this is not a real algorithm. Okay, so we're going to use cost to remember. Everyone would remember cost. Okay, and as long as that you still have nodes outside, now what I do is that I simply says that what is the node that has smallest cost, because this is the cheapest way outside that can reach you. Okay, so now I pick the node with smallest cost any moment. Okay, then I take that node, I remove it from outside. Okay, so that you remember all the nodes you have not yet reached. Okay, so we remove that from outside. Okay, and the predecessor, this node and its predecessor will be a minimal span, because that's how I reach this. So every node, also remember who gave me this smallest cost. Okay, so then its predecessor will be added to as a minimal spanning tree edge. Okay. Okay. Now the difference is that we now, after I added this node, I have to, so I add this node Vj to my set S. So S now becomes S union Vj now. Okay. Once I add a new node to Vj, now there are more edges become crossing edges. Okay. So I need to check. So in other words, a node now will have new ways to reach other nodes. Okay. So I have to check this crossing edge to see whether that gives me a cheaper cost to reach any other new node. Okay. So this is exactly what we do. So now for every, so which edge can be crossing edge? Well, the only change in set S is just we added this new node. Okay, so only its neighbors can potentially be a new crossing edge. Okay, so what we do is that we check all neighbors of Vj, and if its neighbor is outside, then we found a crossing edge. Okay, so this means Vj Vk is a crossing edge. Okay, so now we found a new crossing edge. And if it's a crossing edge and the weight is smaller than what's stored at Vk, that means I found a better way to reach Vk. Then we update Vk's predecessor and also the cost to be this new crossing edge to reach it. Okay, and then let's finish the processing of this iteration and we repeat. Okay, so the algorithm is really the same as before. The only difference is that number one, instead of checking all crossing edges, we now maintain every node, what is the cheapest way to reach it. Okay, and this cost changes when we add a new node to the inside set S. Okay, remove it from outside. So when we reach a new node, we have to update the cost for all the other nodes that this edge can reach through a crossing edge. Okay, so that's what this part is doing. Okay, because we have to update the cost to other nodes. Okay, and this actually, if you compare this side by side with the Dijkstra algorithm to compute the shortest path, this is very similar. The only difference is that there, the cost is the shortest path cost. Here, the cost is just the crossing edge weight cost. Okay, all right. So this is the new approaches. Okay, we're going to look at an example what I mean by this. But first, if I do this, what is the cost? Well, now every time I need to find the minimal cost node outside. If I naively again do a linear, we perform a linear scan to find minimum. If I do that, then I need time, which is order of V. Okay, because there are potentially up to V nodes outside, I have to scan through them. Okay, and this part, the number of iterations in the for loop, okay, is only proportional to the degree of node Vj. So this part only takes time degree of Vj. Okay, so the total cost would now be line 6 has to be, the number of iterations for while loop remains the same as V. Okay, so now I have to execute line 6 V time, and each time take time potentially linear. So then I have a total cost, which is V squared for line 6 plus this part. I cannot, the degree changes every time, but I know that I can only do this. Each node will only be processed exactly once in the while loop. Okay, so this is the, for every node Vj inside of V, and I need the degree of V, this node. Now we know what is the sum of degree for undirected graph. That's 2 times the number of edges. So what we have is V squared plus E. And since that E is at most of V squared in a simple graph, we have this equal to V squared. Okay, so this is time complexity of of this first improvement. Okay, so I have everything written down. Oops, I didn't put it down there. I added the slide. I thought I had the slide. Okay. Okay. So this time complex of this one is the order of V squared, which is still not efficient enough. Okay. But first, let's look at an example of how we change the weight to the vertex. Okay. So let's just use this as an example. Same as before. So now we start. I'm just going to go a few iterations. We start. Everyone has maintained a cost at the beginning. All the costs are infinity. The only cost at the beginning is V1, which this one, which is, let's say, 0. Okay. Now I take V1 from outside, and I start to explore the edges incident on V1. Okay, and when I look at edge V1, V2, that update the cost to be the cost update. So all the time you say that you look at the cost to be the minimum of whatever cost I had was the weight of the edge that's reaching me, of the crossing edge reaching me. Okay, so now V2, the cost update to be 2. V6 weight update to be 3. So in the next iteration, who do I choose? I look at all the costs, pick the one with smallest cost, that's 2. Okay, so now next iteration, I'm going to pick this one. Okay, then I'm going to update all its neighbor to see whether I can find cheaper ways to reach others. Okay, so I look at all the neighbor. One of the neighbor is V1. It's not a crossing edge, so I ignore it. And then another neighbor is V3. This is a crossing edge. That means that I find a new way to reach V3. V3 had cost which is infinity, but now I find a way which is I can reach the through 7 because the minimum of infinity in 7 is 7. Okay. Same, I found a new way to reach V4. So I update the cost here to be 5. Okay. All right. So next iteration, again, I pick the node with smallest cost. Now the node with smallest cost is V6. Okay. I forgot to say that we also remember who gave me this cost. So the predecessor of V6 is V1. Okay, so now I need to explore V6 to see that who are my neighbors and whether I can find a cheaper way to reach them. Okay, so one neighbor is V1. It's not a crossing edge. The next neighbor is V4. And I do find a cheaper way to reach, so it's V4. And the original cost at V4 is 5. So I take the minimum of its original cost and the weight of the crossing edge. So I found a new way, which is 4, to reach V4 through V6. Okay, so I remember the predecessor of V4 to be V6 now. Okay, and I also have a crossing edge to V7. So I found a way to reach V7 with cost 1. Okay, next iteration, we repeat. We find the one that's cheapest to reach, and we add the edge between this node and its predecessor to the minimal spanning tree. Okay, then we say that we need to explore to see whether we can find other nodes. And again, I look at V7, V4. again, the minimum of 4 and 3 is 3. So I found a new way to reach V4, and I remove the previous predecessor. I add V3, V4, V7 to be the predecessor of V4, okay? And I also find a way to reach V8, and so on, okay? So we repeat this way, okay? All right, so okay, so this is now, instead of having the inspect the crossing edges, we kind of put the cost into the nodes, maintain nodes costs. Okay, and every time we find the nodes that we can reach in the cheapest manner, which is the we find the node with the smallest cost. Okay, but as we said, this algorithm, as I described here, if I implement this step using linear scan, it's not very efficient. It takes time. So if the step linear scan, then the algorithm takes V squared time, which is still not efficient. Okay, so can we do better? Okay, at the same time, as I said, you probably see a lot of the similarity between this and a Dijkstra algorithm. Okay, both of them have nodes maintain certain costs. In Dijkstra is the estimate distance, here's estimate the costs. Okay, and both of them every time pick the one with the smallest distance or cost. Okay, so instead, the suggested, and in Dijkstra, we use the priority queue to significantly speed up the time complexity. Okay, in particular, note that the same case in this Prim's algorithm, we just need a data structure to maintain the cost of unvisited nodes, and which also supports we need to delete the node with the minimum cost. That's extract min operation. We also need to update the cost value stored at the node, and the way in particular we will potentially decrease it. If I find a better way cheaper way to reach it, I'll decrease the cost. So I need the change priority operation. Okay, so this suggests that this is all we need in the Prim's algorithm. Okay, this suggests that again we can use the priority queue to help us to implement this algorithm. Okay, so in our case, a priority queue would store key of a node to index the node, and the value refers to the cost of this node. So the cheapest cost of this node, we can reach this node so far. Okay, all right. This is just to remind you that recall that priority queue can be implemented differently, but if we use very standard using min heap to implement the priority queue, then the time complexity to initialize the priority queue is proportional to the size of the priority queue. Extract min takes logarithmic time, okay, and the change priority also takes logarithmic time, where n is the size of the current priority queue. Okay, all right. So here is the final algorithm, and now I'm showing you the Python code for this algorithm. It's using the implementation of Prim's algorithm, which is the same as our outline pseudocode before, but here we use priority queue to maintain all the nodes outside the set U. So the priority queue is maintain set U in our previous pseudocode. Okay, and so we're going to use priority queue to maintain that, and the finding min would be translated to all the operation in priority queue. Okay, so let's just look at the algorithm again. We're given the graph, a weighted graph. Okay, so here I'm also going to explicitly add the tree edge. Okay, so I'm going to represent the tree using an undirected graph. That essentially, which is going to consist of a bunch of edges. Okay, so at the beginning, this the tree only have only nodes. Okay, so and also for every node, I maintain so far what is my predecessor, that is the cheapest way to reach me. Okay, so you have estimated the predecessor for that. Okay, and the cost will maintain that so far what is the cheapest way to connect to a node through a crossing edge. Okay, at the beginning, all of the nodes has cost infinity, so that we initialize them to be infinity. Okay, all right. Now, I don't have to specify any starting node. It doesn't matter. Okay, so at the beginning, all of them has infinity. At the minimum among infinity, which just can be any node inside the set. Okay, so what does the algorithm do? At any moment, I extract a node with the smallest cost. Okay, and if this node, the predecessor is not none, okay, that means that this is the first node we discovered. Okay, so that would be kind of the root of the tree. If the predecessor is none, that means it's the first node we discovered. That means it's the root of the tree. We don't do anything. Otherwise, we basically add an edge between this node and its predecessor that discovered it. Okay, so actually, let me draw a better picture here. So at any iteration, remember that we already found basically all the set S. We have all the nodes in set S already connected. Okay, and then all the nodes outside would remember a cost. Not only it remember cost, it also remember who give me this cost. Okay, maybe what is the minimal way to reach this node so far? Okay, so at the beginning, at any iteration. Okay, so in each iteration, I first pick the node U with the smallest cost. Let's say it happened to be this node. Okay, so this is my U. Then I add the node U and its predecessor to the tree, because this is how I reach this one through the cheapest cost. Okay, so I'm going to include this into my set S now. Okay, so now this is U is added to S, and I added this red edge to the tree. Okay, but I need to now see whether after I added this to S, new crossing edges are produced, right? So I now need to check all the neighbors of U to see whether I can find any new crossing edge to reach other nodes cheaper. Okay, so now I'm going to inspect all the neighbors of U. Let's say that let's say these are all the neighbors of U. Okay, now for each of the neighbor, I first see whether this node is already reached or not. So like this neighbor is already in set S, so this is not a crossing edge, I do nothing. This is not a crossing edge, I do nothing. Okay, this is a crossing edge. Okay, now if it's a crossing edge, then I check, is the weight of this edge, say U and till this node V, I say that is this weight UV smaller than the original cost at V? If it's smaller than the cost at V, that means I found a cheaper way to reach V. In which case, I would say, okay, I update the cost, will be updated to the weight of this edge, and I change the predecessor. Predecessor of V is not, oops. The predecessor of V is not this red node anymore. The predecessor of V instead is this edge UV. Okay, and I do so, I repeat. Okay, then I also see that for each of this crossing edge, I repeat the same. If let's say that originally you had a way to reach this one. Okay, so suppose you look at this crossing edge. If the edge weight of this green edge is bigger than the cost already there, then we do nothing. That means that this new crossing edge doesn't give me a cheaper cost to that node. Okay, and we do nothing. That's it. Okay, so we go through all the neighbors, update their costs, and then we repeat. Okay, all right, that's the algorithm. Questions? Okay, last thing, let's see what is the time complexity. Okay, all right, let's see. This line take time order of log V. Okay, we extract min. Okay, and this line also take time order of log V. Okay, everything else, each line takes only constant time to compute the time complexity. Okay, let's focus on this, how many times is this extract min going to be called? Well, that's the same as the number of iterations of the while loop. Okay, so I'm going to write it here. The number of iterations of while loop. The while loop basically try to reach all the nodes outside. So it's going to run exactly V iteration. Every time we perform the while loop, we reach a new node and remove it from outside. Okay, so we're going to run V iteration and each node will be visited exactly once. Okay, so the while loop number of iterations V. Okay, so this means that number of times, number of calls to extract min is that as such also V, okay? And then this means that the total cost of extract min is basically, you have V iteration, each iteration actually take at most the log V, so it's V log V. Okay, all right, so this step is done. This is just a constant time, so we can ignore because it's going to be only take total cost of order of V, okay? Now, let's see how many times are we going to call this decrease priority. Well, this is inside the for loop, okay? For fixed node U, the for loop, the number of iterations is degree of V, of U. Okay, because I mean, we check all neighbors of U, so it's degree of U, okay? That means that the maximum number of time we're going to call this one for fixed for loop is degree of U, okay? And you can be, essentially, you can be every nodes in your input graph. That means that number of calls to this one will be sum of degree will be smaller than, in worst case, where U is inside your graph, okay? Which make it 2E. Remember the sum of degree for undirected graph equal to 2E, okay? Each call takes log V time. That means that the total cost is order of E log V, okay? And the total cost of the entire algorithm is basically adding them up. So here, this only takes order of V time. All of this takes order of V time. Okay, so the total cost, you sum up all the costs, which is V plus V plus V log V plus E log V. Okay, so the final time complexity, which I put them here, is V plus E log V. Okay. Okay, so this is just exactly what I said in words just now. I put them on slides. You can look at it later. Okay, the total time complexity is basically initialization plus the total cost in extract min plus the total cost in decrease priority. In the end, it's basically V plus V log V plus E log V. And this can be ignored because this is smaller than V log V. So this is the order of V plus E log V. Now, if your graph is connected, so if the graph is connected, that means that E is bigger than V minus 1. Okay, that means that the V is, that means V is in bigger O of E. That means that total time complexity is, okay, same as the Dijkstra algorithm. If the graph is connected, then asymptotically, V is bounded from above by E. As such, V plus E times log V becomes asymptotically E log V. Okay, so this is the final time complexity. Okay, all right, so you can go through this example. I already tried this earlier, so you can check it later yourself. And this is the final solution. Let me see. Yeah, we already ran out of time. Sorry about this. But let me just say one more word, that the Dijkstra algorithm has a lot of similarity from the implementation from the pseudocode point of view as the Prim's algorithm. The only difference is really that in Dijkstra we maintain estimate distance, and in Prim's we maintain estimate cost. Okay, and the way you update the estimate distance is that every time you check a new edge, you say that, okay, the distance will be whatever is smaller, my previous distance versus that the new way to reach U plus the weight of edge UV. Okay, this is basically that new distance of the best path using edge UV, right? This is basically if there's a new path going through UV. Is this new path distance smaller than whatever I found before? Okay, you take the minimum of that. So that's in Dijkstra algorithm. Okay, while in the Prim's algorithm, you're maintaining the cost at each node, which is updated as when you check a new edge UV. It's basically whatever the previous cost was versus the weight of the new crossing edge to reach V, whichever is smaller. Okay, so it's easier to update, but both of these two update takes constant time. So the total time complexity of the algorithm, the two algorithms are the same asymptotically because the algorithm is so similar that here this is pretty much the only difference. Okay, all right. And of course, because of this difference, what you compute is different. In the shortest path, starting from a source node, you're computing the shortest path tree to that source node. Even if you start from the same node, say V1 here, your minimal spanning tree may not be shortest path tree. Okay, so this is just example where minimal spanning tree is not the same as the shortest path tree. Okay, let me just summarize that the Prim's algorithm uses a very similar idea as Dijkstra algorithm. It's a greedy algorithm. We start to grow the spanning tree, okay? And at any moment, we choose the new edge to reach a new node greedily. That's basically the smallest crossing edge to reach a new node, okay? And it can be implemented in time, V plus E log V, which is also same as E log V if your input graph is connected using the min heap implementation. Okay, but the same as the Dijkstra algorithm, you can use a fancier data structure. So if we use the so-called Fibonacci heap to implement the priority queue, then we can actually improve the time from E log V to be E plus V log V. Note that E doesn't have the log V factor anymore. In general, the graph E is bigger than V, so this is better than this. Okay, all right. So that's all we want to talk about today. Next time, which is after midterm, we're going to talk about another algorithm to compute minimal spanning tree. Okay, that's all for today.